What's up, guys? Just finished up this Vyper audit, and one of the hardest things auditing a code base this big is just kind of getting your head around the whole thing and how the different pieces work and what they're for. Now that I've spent a few weeks deep in it, kind of meshing it with my brain, I figured it'd be useful to brain dump a little bit of that kind of like technical walkthrough of how it all works, so that anyone looking at this in the future can kind of get a head start and not spend as much time on that piece as I did. Uh, so I think what I'll do is just dive right in and kind of go through kind of how I did like the first pass of making sense of it. If it makes sense, I may veer off and explain a little bit about tooling setup I used and how I structured testing, um, and maybe a little bit about some of the loose ends that I wasn't able to have time for that might be interesting to explore in the future. So let's get started. So if we look at the Vyper repo, we can see there's a file setup.py that's run when it's installed. And this is what holds the entry points. So if we see like when you're compiling using Vyper file name, it's calling to this place. So let's jump there. And so this is the argument that everything's getting passed to. And if we follow that along, we can see that basically this is like standard Python parsing where it's grabbing a bunch of arguments to that CLI call. So version, this is the Vyper version. It's not actually setting it here as far as I could see. It's there's like a check later basically because you're only running one Vyper version, right? So it's checking to basically make sure those align and reverting if it doesn't. Showing gas estimates, that just kind of sets a flag so that gas, throughout a lot of that compilation process, it's gathering it up and changing how it prints it out. Formats, this is all the different formats. We'll come back to this later, but basically we're going to put together like an array of formats to output, and then the compiler will go through its whole process, saving all the things it needs to save, and then kind of give you back all of those different things. Those could be intermediate representation, the bytecode, opcodes, assembly, anything along that process. Storage layout file. So because there's no inline assembly in Vyper, we can't do like an assembly block where we would manually set a storage slot. So to do that, we have these kind of storage files. Here, I'll show you an example where we have a variable kind of type and then what slot it should go in. So we can pass those as arguments to the compiler and it'll make sure those things are in those slots instead of the usually defined ones. EVM version. So this is like Paris, Shanghai, like what functionality and basically like what hard fork it should be supporting. Optimization. So there's a few ways to optimize. They've got this no optimize flag. I think they're going to get rid of this. But this optimize flag kind of lets you pass none, gas, or code size, and it'll go down different branches based on those. Okay, I don't need to go talk about debug. No bytecode metadata. So at the end of most Vyper compiled bytecode, there's like a chunk at the end that basically specifies like the compiler version and a few other things that aren't used by the program. They're just kind of there as a tag. So that would be a way to turn that off. This is just reporting. This is just reporting. JSON, this is like just an output format to kind of output all of the different formats together in one JSON file instead of choosing them. If we want to print the intermediate representation, do we want the numbers in hexadecimal versus normal decimal? Path, output path. So that's it. So those are the things we can input to the compiler. And then here we're just kind of grabbing all those and putting them into the right variables and kind of getting them organized so that we can call compile files. And if we look, why is that not going? There it is. I mean, this is all just not super specific to Vyper, but we're grabbing the source code. If there's storage layouts, we're grabbing those storage layouts and saving them as a dictionary. We're setting the formats that we want. A few that kind of had old names that we want to translate to new names. And then finally, we're calling this Vyper.compile code. So this is like the main entry point for actually doing the work in the compiler. So everything here was just kind of gathering up the right arguments so that we can call this function. And okay, let's just jump straight in there actually. This will actually be in, let's go in this way. It's going to be in compiler. There we go. So this is the function. So if you're kind of starting to explore this, this is the place to start. And we can see we're passing the like strings of the source code of what's being compiled, a list of all the output formats. That's just for handling exceptions. Code for the interfaces that we're importing that we want to make sure we're implementing. We don't really use that. Settings is like optimization version, EVM version, storage layouts if we want to show the gas estimates and if we want to put the metadata. So like that's everything we need. So if we come down here, we can see we're just kind of like iterating over the different contracts to compile, and then we're creating this compiler data object. So if we check that out, we can see that this is a class that holds all those basic same things we spoke about, but this has properties that basically define how to get all the different steps of the process. So we can see there's like a generate AST property or like function that is cached as a property that does all the work to make the AST being like the abstract syntax tree of how the program runs, and then returns it. Same thing with creating the intermediate representation, right, and returning that. So this is kind of where all the work is done in this class. And then basically once we have that and it's done the work, we're going to go through the output formats that we defined, and then we're going to call like that formatter is what we want. So if we look in this output formats dictionary, we can see that like for each string of an output format that we could have defined, there's a function here that defines what to return for it. So if we jump back, we're basically saying like compile the code, and then, or not compile the code, create the class with all the data for the compiler, and then for each format we want, like go through and do all the work and return it. So if we go in here, these functions are the functions that define everything we want to get back, right? So the default is bytecode. That's like if we don't say anything, we're just getting back the bytecode. And we can trace back to say like, how do we get the bytecode in order to see what steps are actually done. So we can see, okay, first thing is it's calling compiler data.bytecode. So where's that coming from? Okay, that's a cache property. And a Python cache property is basically, it's a function that we can call like it's a property. Easiest way to think about it. So that calls generate bytecode. So we can see, okay, that's the last step of the process that we're going to want to understand. But what's going into that? Well, it's calling self.assembly, another cache property. And if we go back and saying, okay, that's calling generate assembly using the IR nodes, that's intermediate representation. And if we look at IR nodes, that's calling IR output. How do we get that? Okay, that's calling this generate IR nodes function. And that's taking the global context. And if we jump back, that takes in the folded module. Folded module takes in this folded module, which is calling this generate folded AST. And if we go back from there, we can see, okay, well, how is the normal AST generated? It's with this function. So we kind of just zoom backwards through the whole thing. But what we can see is basically starting from the source code, we're going to do this function, which is generating the abstract syntax tree and like setting some optimization stuff. Then once we have that AST, that will basically be passed into generate folded AST. That's going to do some work on folding, which is like compile time up, like stuff that can be done to save runtime work. We'll go into that in more detail soon. So then once we have that folded one, we have that's passed to generate IR nodes. That's going to give us intermediate representation. Then that's passed to generate assembly, which is going to give us like the pure like assembly, like in words with a few things not quite in bytecode. And then we're going to generate the bytecode with that. And finally, this output is just going to pass it to us as a hex string. So that's kind of the zoomed out overview. I have these, let's see, where are they? These 3 articles on the first day I read were helpful for me in kind of getting my head around it in a really zoomed out sense. So I'd recommend like starting off just reading this. Obviously, like we want to get into a ton more detail with a lot of these. This one's particularly very good, except it kind of skips a lot of the meaty stuff at the end. So it goes to a great level of detail on the abstract syntax tree and folding, but then kind of just jumps to like and then we turn that into IR and optimize it and make it bytecode. So I hope he makes another one that goes deeper here. But this is a good overview to get started. And then this one was very, very good as well as like a deeper introduction and understanding of the language and just like a more readable, intuitive way to understand a lot of what's in the docs. And then this was great as well, just on like a pure like how does the language work level. So reading those three, you kind of understand the flow of what I just explained in terms of the different steps. But what I think is useful for this video is just to dive into all of those steps individually. So let's start with, and I'm gonna just peek back and make sure I'm not missing things. I've got on my wall here my big overview of everything that kept me grounded through a lot of this. So yeah, so perfect. First thing we want to do is generate AST. Find it there. Okay, great. So if we start at this generate AST, what this whole chunk is trying to do is it's trying to take in the source code and it's going to turn it into an abstract syntax tree, which is basically a nested set of, I'm going to butcher this, but I'll explain it the way I understand it, nested set of like operations or values that explains the logic of what all the code is doing, like completely, but in a way that is easier to kind of like reason about or manipulate or play with later, or for the compiler to understand. The way that Vyper does this is really clever. Python has a module that does abstract syntax tree parsing, and Vyper obviously has a lot of overlap with Python. And so what is done is there's a little bit of work done up front to change some of the Vyper code to make it align more with Python code. There's some like annotations saved in terms of like which of those changes were made. Then we just use the Python AST parser to parse the code from there, and then we change some things back based on what we annotated before. So it's kind of like saving some of the state, use the Python parser, come in after and tweak it, which is very clever and means that this code itself doesn't have any like risk in how the tree is parsed, assuming you think Python's is fine. So if we go into that, we can see in this phases they call to vyast.parse to AST with settings. So this is, we are now in this AST folder. So if you're looking at the Vyper repo, you'll see that's one of the folders. This whole folder is everything that's involved with going from source code to that abstract syntax tree. So let's go through the steps. So first, we're calling this pre-parse. And if we jump in here, I'll show you what it does. It's basically going through the contract and making sure that a lot of the stuff like the pragma line and stuff are all set properly. So if we check this out, in the comments, so that's where it's looking for the pragma line, it's going to grab, did we say a version? Did we say a pragma? Did we try to optimize or like set the optimization level? Did we set the EVM version? If any of these are set twice, it's going to error. But the other thing it's going to do is call up to validate that version pragma. So you can see here, it's going to go and basically use this this like specifier set that is kind of from Python, not from Vyper specifically, and it's going to set up based on the version that was entered there, and then it's going to check the version that is actually being run against that version to make sure it fits. I played with some ideas for issues here, because one of the quirks of this specifier set is that if we get it to pass an empty string, then everything will pass. So I was trying to figure out if there was an issue there, but it looks like it's well covered to make sure that it can't be zero and it's stripped beforehand. So that's one thing pre-parsing does. The other thing is it is making sure so the way that Vyper does that kind of like translation before is it takes log statements and kind of like constitutes them as a yield, because yield isn't used. And then it takes interfaces, structs, enums, and events and puts them all as classes, because that like fits the logic of what is going to be parsed. So first it's making sure we don't actually use those, because then they would accidentally get carried through, and then it's going to kind of translate all those things over and make this modification offset struct that holds where the values that were shifted were before and what type they were, so we know when to shift back. So that's the pre-parsing. Let's jump all the way back to, oh, there we go. So once it's pre-parsed, then we're going to just do this Python AST.parse, and I'll show you, like, Python AST here is up here. So that's like Python's AST module. And this is like straight from that library. So we're going to assume that works fine. This add function node is a little funny. It's not used right now, so it'll be passed as none when the main thing is being passed. But occasionally, like in some of the built-ins, we call back and recompile like little chunks of code in order to know which intermediate representation to stick in those built-ins. And we don't want that to do a lot of the analysis as if it's the top level, because at the top level, we're doing a lot of the semantic analysis to make sure like there's no variables declared twice and constants are declared the right way and all this stuff that doesn't apply to a little snippet of code that's being plugged into a function. So if this is the case, it kind of wraps it in something so that it's not misinterpreted as the top level. Annotate Python AST. So now we're going to go back and do that annotation. Let's see, how much detail do we want to go into here? Basically, we're going through and like adding in like the where in the source code it is. Like a lot of this stuff is useful when there's an error to kind of like highlight and show where it was. But we also want to be annotating a lot of the stuff around like what the previous type was and that kind of thing. I didn't spend as much time on that annotation, so I don't have quite the level of detail. And then the last thing here is to actually like translate it into a Vyper AST. So if we run through here, we can see this is kind of a like recursive thing where for each type, it's going to call back in and kind of parse it a little bit further. So we can see like implements is getting replaced with assignments. Same with variable declarations. It's just kind of going through and like putting it into the right language to work as a Vyper AST for the rest of the process rather than the Python one that it currently is. This actually may be where things are shifted back into like events or structs as opposed to classes. This was like the very beginning of what I worked on, so it was probably 4 weeks ago now. I don't have quite the memory. But it's also just making sure here there's some types that are not supported in Vyper, but they could have like squeezed through. And what they don't want is for you to write like disallowed Vyper, have it parsed properly by this Python AST, and then somehow sneak through and do something destructive. So that's just kind of checking for a lot of those. Cool. Okay, so it's going to return that. So after all of that is done, we now have this AST. And what we can actually do here, I'll show an example. So if we do f AST, this was beautiful. That kind of argument -f that lets you return any type. It's really easy to kind of inspect these things partway through. So I had this kind of minimal one set up, and we can see it's just returning these like huge, like basically dictionaries of nodes with types, and then kind of subnodes all the way down. Cool. Okay. So now we can go back to. We'll just go to phases. Cool. So that's generated. It's going to do this check on the EVM version. This is actually, I found an issue here where the EVM version, if it's specified in the file, actually doesn't, or no, sorry, in the argument, doesn't actually get passed through because of the way that context is set up globally. It's like too late for it. But they're trying to check here for making sure that the EVM versions match, the optimization levels match. Basically, if you set something in a contract and something in the CLI argument, making sure those are equal, or otherwise it reverts. And then if no one set any optimization levels ever, it sets this default, which is it defaults to gas. Cool. Okay, so we have an AST, but it's unfolded, right? So the next step of this process is generate folded AST. So we're going to pass in Vyper module, which we can see here is just the AST that's returned. And we're going to generate this folded AST. So this does a few different things. It's going to first do some, let's see, let me remind myself. Yeah, some validation. And then it's going to call this fold where all the magic happens. And folding is basically saying, like, okay, if we declare a constant, let's just plug it in all the places so there's not more stuff to do at runtime. Let's do some literal operations to take care of them now. Basically, like, what's all the stuff that we can do right now at compile time that we know is rock solid so that we don't have to add more runtime work later, because there's gas cost later and there's not gas cost now. So this is kind of like validation all the way down through the AST. And we can see, so it's grabbing all the descendants, that's like everything down the tree, and it's calling validate on each of them if it has this validate attribute. So let's see, what's the easiest way to grab that? If I just say validate, it'll take us to some. So there we go. So like if they're numbers, make sure that they fall within the bounds of what they should. If they are decimals, make sure they fall within the decimal bounds. If it's a hexadecimal, make sure there's no underscores and that the length is multiple of 2. You know, these are like very basic things to catch early. There's a lot more validation that happens later, but this is like the initial stuff. No empty tuples, that kind of thing. Cool. Let's see. Where was I? This is one of the challenges with this stuff, is it's easy to get lost. Cool. So actually, you can see I wrote myself notes here of all the stuff it does. So insert within the bounds, decimals, hex, even number of characters, no underscores, ASCII strings only under 256, no empty tuples. Perfect. So now we're going to copy the whole module over. The reason we copy it is just that we want to, if someone has entered that they want the unfolded AST as one of the things to return, we don't want to change that in place. So we make a copy, and then we call this fold. And we can see I took notes for myself here, but actually, let's just go into it. So this is going to go through a number of things, and we'll see this same kind of pattern in the optimizer where there's a number of specific things we can do, and we're going to just kind of go through them until we can't go through them anymore. So first is to replace the built-in constants. So we can see built-in constants here are like these different strings that you could put right into the source code. And it's going to go through each of them and just basically say, like, replace constant is like, just like sub it out for what it should be subbed out for. Then we are going to go through these 4 things, and we're going to do them in a way where it's like, we do each of the 4. If anything changed, then we're going to go back to the top and do the 4 again. And basically that's a way that, like, sometimes some of these things unlock another one. We don't want to just do one pass. So we're going to just keep going until there's nothing changed, and then we're ready to move on. So the first thing we'll do is replace user-defined constants. So if we've got kind of at the top of here, if we've got something here that's like x is a constant, u in 256 is 6, and then down here in a function, say like function, if we said like return x, okay, so in order to make this simpler, it's going to just go and take 6 and plug it right in there when it compiles. So like the constant basically disappears and the number gets added here. And then they erase the constant after. This is actually another issue, or it's a small issue, that I found that when it does that replacement, it skips any tuple constants, which I don't know if they're even supposed to exist, but it skips doing anything and then it deletes it. So it just doesn't exist anymore. It's not actually a big deal. Weird thing with compilers is like things that cause errors at compile time are not nearly as bad as things that squeeze through. So it deletes this constant and then it can't find it later. So it just won't compile. But anyway, so it'll replace all those. Then it's going to replace literal ops. So it's going to go through the whole tree and look for any things that are like addition subtraction, multiplication, whatever, or not, inversion. You can see the list here, comparisons, and it's going to look if both sides are literals, if they're like numbers that were plugged into the source code as opposed to variables, and that includes constants, right? Because we've replaced them now with literals. It's going to actually do the operation and put the answer back. So we can see if we go in here, it's right here. It's going to go through and just replace those straight in the tree, and it's calling this evaluate method. So if we call evaluate, we can see, let's not do it on the functions, it's on the nodes. So for example here, let's find an easier one, a binary operation, perfect. So it's going to say left and right, they have to be the same type. If it's not an integer or decimal, then that's not going to work. And this unfoldable node, it doesn't actually raise an error. There's a try catch for it. So that's basically saying it can't be folded, just skip it and don't worry about it. And then it's going to, let's see. Yeah, so this is like grabbing what the operation is and then doing that operation on the left to right things, validating that the number's in bounds, and then it's just going to replace it. And when I'd say like the type of operation, like add is an example of that, whatever. So yeah, it's going through, and like I said, unfoldable note, it'll catch that and just continue. So we're replacing all those in the tree. Then we're going to replace subscripts. So subscripts being like going into the index of a list, or yeah, I guess that's it. Or yeah, I guess dictionaries too. No, probably not dictionaries actually, because you wouldn't be sure. Anyways, doesn't matter. It's going through any of these that have subscripts. So like a array with an index at the third place, it's going to check and say like, is that a literal list that we know the list already? Let's just grab that and replace it in the tree as well. And then the last thing is replacing built-in functions. So there's this folder, this file, which is all the functions that are like built into Python. So you can actually see a list of them here. That's all of them. Or if we go to Chrome, we can just say like Vyper built-in. I'm sure I've been to this page way too many times. So this is all of them, the like built-in stuff. Some of that is like slices or bit shifting, hashes. Some of them are like ways to deploy contracts, converting between types, that kind of thing. So this is like, there's a lot of interesting stuff here. It's where many of the issues I found were, because it's kind of, I don't know, it's interesting to look at because it's kind of like writing source code in a way. So if you find issues in it or edge cases, those can be problems. So some of these, here, let's find an example of one. Right? So these usually have two methods on them. Evaluate means like, can we do this at compile time, right? Like the section we're in right now, it's looking to call evaluate, and it's saying like, hey, if we have literals for both sides of this, we have literals for length of x and x is literal, let's just plug in the answer. Build IR is for later when we don't know exactly what x is going to be, how it creates the intermediate representation that gets plugged into the actual code. So if we look here, we can see evaluate. All these evaluate functions are ways that built-in functions could be evaluated at compile time to just replace it with the answer as opposed to even having the function in there. So I won't go through all of those right now, but it's going to go through each of them and look for where it can see it's looking. Does it have evaluate? If it doesn't, skip it. If it does, do it. Otherwise, if it can't do it right now, skip it. Great. So that's kind of the loop it's going to run. Let's just go back to phase. Here we go. So it's going to say, replace those constants, do literal operations, replace indexes into literal arrays, try to run the built-in functions. If any of those changed, do it again, and just keep doing that until it's 0 at the end. So that is folding. Let's see, I guess. Now it's going to validate semantics. So you can see here, I've kind of got the steps laid out from notes to myself, but it prepares a namespace. So then it does this at the module level. So module level namespace is like the very top level. What are the function names? What are the variable names? Just making sure all of that is validated. And then it's going to go through any variables that are tagged as or I guess that have an external decorator that's tagged as is public internally, and make getter functions for them, adding those back into that global namespace. It's going to get rid of some of the stuff, like if checking if interfaces are implemented. It's just going to check if it's true and then get rid of it. It doesn't need to put it in the source code. Same thing with constants. We've already folded them in, so we can just get rid of them. And then it's going to go through each function and validate that like they follow the rules, that if it's pure, if it's payable, its local namespace is consistent and doesn't have variables that shadow each other, that kind of thing. So we can pop in here quickly and just loosely see how that works, but we're making this namespace, and then we're going to do this module level namespace, right? Here's the class that does it. And a lot of it, like, it's a lot of this like recursive logic that goes down the whole tree, calling this visit, that does a lot of the work. Do I want to go into? Yeah, let's do it. So when it's calling this visit, it's going to go here. Let me see, I'll show you how this works. So it's going to look, and it's going to look at the type and then call the function that's visit underscore that type. And if we look down here, we've got all those types. So like when implements shows up as it's going down this AST, it finds a node that is an implements node. It's going to visit that and then do this validate implements. So it's going to kind of like follow this set of rules to check that that is true. Then same thing with variable declarations, and basically all the things it can find, it's going through and validating there. An interesting bug, I found something with implements. If we go here, you can see that if there's a function and it's public, or I guess if there's a variable that is public, so it's going to get turned into a function, then it says like, great, this passes. But it doesn't check whether the thing it's supposed to be implementing is payable or not. So you can end up with an interface with payable functions that like view functions on your contract like check the box for, but they're obviously not payable. So that shouldn't work. Anyways, that's just one example. Lots of interesting stuff here for how variables are validated, events, enums. So like enums is another example. It's just kind of like this. This kind of confused me for a second because I was like, wait, it's just setting this. Like you could override other names, whatever. But if we look at this kind of like set item in namespace, we can see that it's first like validating that it doesn't exist and then setting it. So it actually would error otherwise. Let's see if there's anything else that I remember is interesting from here. Imports, there's some, I would dive into imports more if I had more time. There's definitely some like some weirdness there. And also part of it is just me not knowing the typical Vyper syntax. So like one weird thing, if you write an interface in the file, obviously it's a different format than if you write it in a different file. So in the file, it's got this very specific format. If you do it in a different file, you're supposed to write it as like normal Vyper, and just you can write pass for all the functions. But if you take the format that's supposed to be done in the file and do it in a separate file, it like sneaks through a lot of the checks and looks like you're doing something, but it's actually not doing anything. I don't think I submitted that because it doesn't really feel like, it feels kind of like a user error, but it's kind of interesting. Cool. All right, that's good for that. So then let's go back here. It's going to expand that annotated AST. Let me look on my wall, remind myself what that even is. Oh yeah, perfect. Okay, so that's adding all those getters that we talked about. Yeah, there we go. So adding getters, it's going through all the variables that are public and going through this process with them of like basically turning them into functions. And then it's going to call remove unused statement. So it removes that implements and removes the constant variables. And then finally validate functions. So it's going to go through each one by one, validate the namespace, validate that it returns what it should, follows the pure and payable rules, go into each of the nodes and make sure like they're following the rules too. Yeah, let's skip this. So then finally, we're going to set the data positions. So this is going to basically be using that storage layout that we passed as an argument if we did, otherwise doing it itself. And that's trying to grab like the layout of which slots are for which variables and then where mutables are in code. So if we jump in here, we can see this code offsets, it's grabbing all the immutables and saying, okay, if it's immutable true, then let's kind of figure out how long it is and then figure out where it's going to sit as a code offset. And then for storage slots, if we've got the overrides, we're going to use this one, which is basically same logic as the other, just validating that we're using all the variables that we are supposed to, or set storage slots, which actually allocates them. First, it's going to look at all the functions and say, okay, if they've got a non-reentrant decorator, then let's go through and assign them. So just a kind of interesting thing, the big Vyper bug from this summer, where there were issues with non-reentrancy. Basically what was happening was if you had different functions with the same reentrancy lock on it, they would actually be put in separate storage slots. So I could go into one function, get a callback, and then still reenter into another function. So if we look at this chunk right here, we're saying, okay, if it's already in there, just set it to the one from the dictionary and then move on. If we took this out, which I don't think is exactly how the bug happened, but something along those lines, then we would be reallocating each time, regardless of the name. And that would cause that same problem. So we're going to just be allocating slots for each of those reentrancy locks. And then we're going to go through the variables, do the same thing, right? Skip the non-storage ones. And then for each one, get how big it is in words. In Python or in Vyper, it's nice. We can do that because everything is statically sized, and then allocate those slots and return it. So this return thing will be all the types, reentrancy or storage, and which slot they correspond to. And then we're going to return those two things. And that takes us all the way back into phases. And let's go back here to where generate folded AST is called. Here we go. So we've now taken our source code. We went through the kind of AST pre-parsing and parsing into this Vyper AST, and then we did all the folding. So the folding was a lot of that like validation work, as well as the actual folding to make things more efficient and setting up the storage layout. So we've got all of that, and then we've got this kind of weird pass through where like Vyper module folded is just that, where we just ignore the storage layout. And context is just a different class, but with that module, which is what we just created that was folded as something that's accessible as the module in there. So this global context is like everything we have so far. The next step, so we've got all that. We've got our parsed and folded AST. Now the tricky part starts of generating the intermediate representation. So if we go here, we can look at this. Oh, not that one. This one. So this is the page on there. Read me about Vyper IR. It's pretty easy to understand. It's very similar to just like what you would expect in assembly, like a lot of the opcodes with just a little bit of extra around it. The way they do it is there's these kind of like chunks and parentheses, and it's not ordered the way you would have to like push this onto the EVM stack, push this onto the EVM stack, then perform an operation on them. It's more logically added. So if we did like add, it would be like add 1, 2, and that would end up being compiled as like push 2, push 1, add. So this is kind of like an overview to understand what things are supposed to do. And let's get into what it actually looks like. So we are going to do this generate IR for module. So that's like creating it, and then we're going to run it through this optimize function. What you can see here is the optimizations for code size or gas are the same, right? It's just saying as long as it's not none, we're going to call the same function on it and then move on. So we're really just doing two things here. So let's get into this. This is probably the meatiest part of the whole code base because we're taking the syntax tree and we're making it into something that like is pretty clear how it's going to become EVM bytecode. So let's see. I'm going to try and figure out what level of depth is worth going into here. You can see a lot of print statements and notes to myself from when I was figuring it out. So first, we're going to sort the functions. One thing that's nice in Vyper is there's no like circular calls. So you're able to just go down the tree to the bottom and know the order that like this function will always be called before this function, or like this could never be called without it coming from a different direction. We can kind of like see the whole tree of calls that are possible. And obviously there's two external functions call the same internal one, or lots of things like that, but we can never have function A call function B and also be kind of like below it on the tree, right? It's all linear, which allows us to kind of do this sorting. Spent a bunch of time feeling like I could break this, and I was wrong. So it's basically going to go through each function is like holding the functions it calls, and it's going to go down that tree and make sure that it's got them organized in order. Let me just make sure what the order is, whether it's top to bottom or bottom to top. I guess top sort would imply top to bottom. So now we got all these functions. We want to split them into which ones are internal, which ones are external, runtime, init, like constructor stuff. So this is just taking that list of function defs that we have here, saying, okay, any of them that are not the constructor, we're going to put in this. Any of them that are the constructor, we're going to put in this. Then we'll split the runtime ones into ones that are internal, external, but not the fallback, and the fallback. And if we look, these like look like they're functions, but they're just saying like, is the metadata saying it's the constructor or not? All this stuff is parsed right from the source code. So then we're going to start by going through the internal ones. And we're going to create that intermediate representation. Lots of nested calls here. It's going to check that there's just one exit. So it's making sure there's not like one path that has two return statements where the ones after it would get skipped, or a return statement with more code after it. And then we're gonna, so the way that memory is allocated is kind of interesting and definitely made me think I was gonna find something, but I wasn't able to. So now we've got all these functions called in order, right? And so I'm able to say, if you call function A and that calls B, which calls C, and it also calls D, I can basically allocate the memory for each of those subcalls and say, okay, B is gonna own like this slice of memory, and C is going to own this slice, and D is going to own this slice, and then we don't have to like clean up the memory in any way, right? We just like leave it all there and know that each call is only able to access their slice. So this is kind of going through and saying like, what's the biggest amount of memory that each of those could use, and let's stack it all up and reserve it and kind of like keep it organized that way. Then if it's internal, so let's start with this. We're assigning the new variables. You can see here, this is just, I'll show you. It's creating this variable record and allocating memory, right? So it's like taking the slice of memory and saying like, this variable is attached to this section in memory, and making sure that it fits in the bounds and that kind of thing. We're going to create that non-reentrancy lock intermediate representation. So this is going to be the first time you see like IR actually being generated. So we can see, okay, we're setting these values, whatever, and then here's what we're actually returning. We're saying assert not equal temp value, which is the one that should be set, like what it will be set to while it's not reenterable, to loading the key of where it is in memory. So like this is the actual IR code that will do the reentrancy check for you, or like that will check that it's not set. And then all of it put together will be like, here's a sequence of things. First, we're going to check that it's not set. Then we're going to store the temporary value. And then after, we're going to store the final value, right? Like we know what reentrancy does. But that's the actual like creation of the code that will end up being used. One thing, this was my most frustrating moment of this, it's not in this file, but I've got it somewhere else, is this check, if not, Well, in Python, an empty string is considered not, right? Right, there we go. We did it. So you can guess what that means is if we did non-reentrancy in this way, here, let me show you an example. If we did at non-reentrant that, I can't spell. That's a bit of a problem. There we go. So if we do that, if we look back here, that's going to trigger that, and it's just going to make no IR code. So this is my first like very excited finding, and then I found that it was actually a security advisory from a few days after the contest started. So it had already been solved. So I didn't have to worry about reporting it, which I'm glad they were able to find that. So we're going to make that pre and post. We're going to do a bunch of work here to like set things up, and then basically we're going to do the non-reentrant pre, parse the body of the code. We'll get into that in a second, and then do this cleanup routine where we're like knowing where to exit, like which program counter to go to, because this is an internal function, so we're going to go back to an external function, and then that non-reentrancy post too. So basically, we're like doing all these things to put together all this IR. We're gathering it together, and then we're returning the body and the cleanup routine as like one big sequence of things to do that represents this function. So if we go into parse body, this is like where all the meat of this is. It's going to take you to this parse statement, and parse statement is creating a statement class or an instance of the statement class, and that we can get into all this, but mostly it's calling parse underscore type. So the same thing as the like semantic validation was doing, and we can see that's parsing expressions, parsing pass statements, parsing names, parsing assignments. And so it's got, basically this is where all the logic is, where it's saying we've got something that has to be parsed. It's part of a function. And then once we're in that function, we're going to parse all those individual pieces into the intermediate representation that captures what they do. And then we're going to put it all back together and return that as representing the function. And then later we'll put all those functions together as representing the contract. So as an example, I don't think it's even possible to spend the time to get into all these. This is where a lot of the time was, but we can see it's like, let's see, make setter. This is like where a lot of the assignments are. So this is like a lot of time and juiciness of like, okay, if we're trying to say we want this variable to hold this one, how do we manage that? If statements, so we can see like it's parsing the expression, and again, it can't like parse this at compile time, right? There's no literals in it. So when it's saying like test expression, it's trying to, let's see, expression. Yeah, so I'm not remembering exactly how this works right now, but basically it's like creating the intermediate representation for that test expression so that the body can be if, and then the test expression, and then the body of the thing to do. And then the add-on if there is one, if there is an else statement. And again, that other body then just goes back into that same loop of saying whatever is in there, let's parse it. So this is used for calls, and anything that's a built-in function is this call, right? So it's going to say, okay, if it's just a name, that's saying like it's a built-in function, then go to this dispatch table, find the function that represents it, and call build IR on that. So that's how those built-in functions intermediate representation gets into the actual code, is in this little chunk right here. Let's see, append calls. These are just like unique things that are represented as calls. If you do like dot append, you want to handle those in a specific way. Let's see, assert reasons, what other? Assert, raise, for loops. So it's just parsing it as like a little bit differently if it's saying like for a range versus iterating through a list. And all of these are held as, if we look in Vyper IR, you can see how repeat is structured. So this is like how they do loops in Vyper IR. So it's kind of like translating it into that mode. Assignments, aug assign is like plus equals 1. Break, return. Yeah, we'll leave it at that. So all of that is parsed into the body. So like we said, this is like one, how do we make an internal function? We're going to get that reentrancy lock. We're going to parse the body, which could be anything, right? But it's going to put all that together. And then it's going to put together this cleanup routine with the reentrancy lock if we need it, and put all that together. So now we've got this, like what represents the internal function. Let's get back. Oh, God. In here. Let's go one further back. So we're going to do that for internal functions. And then we're going to do the function dispatcher. And so that's going to look different. If we have optimization set to none, it's going to do linear, which is just like we've got our 4-byte selector. That's like the first 4 bytes of the call data. And we're going to go through and say, does this match this? Then jump to this point. If not, then does it match this? Jump to this point. If not, all the way through. And if none of them, then go to the default, like the fallback. So we can see that logic here. What's interesting is these function selectors, like this logic, also includes the logic for making all the external functions. So like you'll find that's missing, but if you go into it, you can see like generate external function entry points. So that's going to go through, make that internal representation for every external function, and then come back and build this dispatcher, which is basically just saying for each one, do that check, do checks that the call data size is sufficient and that it's payable or not payable is correct, and then put all of that together into like a big block with all the external functions and the dispatcher that points you to the right place. So that's like the linear one. The interesting stuff here is there's 2 other dispatchers they've got now. One is, this is the kind of like default that happens if you're just optimizing for gas. And then this is if you're optimizing for code size and you have more than 4 functions, they added some extra logic. So let's go through these because they're really fun. So this is going to create all of them, and then it's going to create these buckets. And so what it does is it creates, let me make sure I haven't looked at this in a few weeks. I gotta make sure I get this right. I was deep in this for days at one point. So we're going to go through, so we're going to go through and we're going to take each function selector and we're going to pick a number that's somewhere between, so say we've got 10 functions. So we're going to start at 8 and go to 12, and we're going to go through each of those numbers, and we're going to make buckets for each of them. And what making buckets is it's just taking the modulus of the number, right? So if we've got 10 functions and we want to try with 8 buckets, so we're just going to take function selector mod 8 for all of them and see how many buckets we end up with. And how many functions are in each bucket, right? So if we said mod 8 and we ended up with 1 bucket that all of them were in the same bucket. So all 10 functions ended up with the same value, mod 8, just by coincidence. We don't want that. That's like the worst case scenario. What we want is them to be spread across the buckets. So we're going to go through each of them and look for the let's see, the max. Right, we're going to go through and basically pick the one that has the smallest, biggest bucket, right? That the max bucket is smallest. Okay, so our strategy here is going to be, we're going to enter at the top of the bytecode, and we're going to take the first 4 bytes of the call data, so the function selector, and we're going to take it modulo the number of buckets. So that will tell us like which bucket this function belongs in. And we're going to pick the spot for us to jump in code based on some predefined value that's like the end of our actual code, plus which bucket we're in times 2. And that's going to tell us which 2 bytes we want to grab that represents that bucket, right? So we might have like bucket 0, the code ends here, then we've got bucket 0, the first 2 bytes, bucket 1, the next 2 bytes, bucket 2, the next 2 bytes, all the way through. And we're going to copy that 2 bytes from the code into memory, and then we're going to jump to that place in the code, and then we're going to do the normal linear process where we just check, does it match here? If not, does it match here? All the way through. So ideally, we have one thing in each bucket. Every time we jump, we get straight to it, and it's like O of 1. But sometimes there might be extra ones in there. So that's kind of the logic here, right? We're copying the code from that destination point, to the destination point, which is like the last 2 bytes of the first word of memory, from the bucket header location, which is the start place plus the bucket ID times 2, and we're going to copy 2 bytes, and then we're going to load it and jump to that place. So that's the sparse jump table. And then once we're in that place, we're going to do the normal checks: call value, call data size, all that stuff. One interesting thing here is we also need to check. Yeah, we need to check that they match, even if we land on one that's just that one, because otherwise a random function selector that happened to have the same modulo would just send us to the wrong place. So that's the sparse one. And then the really fun one that I'll hurt my head trying to remember right now is the dense one. So what that does is it looks at compile time to find like a magic number that actually splits them all perfectly. So there's not, because if you think about this sparse one, you could have wasted code at the end, right? So say we end up saying the best thing to do here is to have 40 buckets, and 10 of those buckets have 2, and we have 40 functions. So 10 of those buckets have 2, 10 of those buckets have 0, and 20 of the buckets have 1. And so that's what we put. Well, now at the end of the code, we're going by number of buckets. So we've got 10 times 2, 20 bytes that are wasted that we'll never jump to, right? So what the dense thing does is it looks for this magic number that will make sure that the selectors at the end are exactly like one place to land for one function. And it does that here. I'll pop to the logic quickly. So we're going to basically try generating this dense jump table info based on the number of buckets. So it's going to do this like same thing, but the number of buckets that we use here is going to be like descending, right? So we start off at this kind of like randomly chosen start point, and we're going to keep going down by 1. And so we will do this. We'll make the buckets, and then we'll do this check after to see if there's a magic number. And the magic number is what number could we take where we take the method, or like the 4 bytes for the function, we multiply it by this magic number, we shift it to the right by 24 bits, and then we go modulo the number of functions we have. And what we want is for every single one of those to land on a different number, right? So we've got 100 functions. We're taking it modulo 100, means we have 100 options. They need to match 1 for 1. So it's pretty unlikely, but if we look at this find magic for, we can see we're trying every number up to 2 to the 16, so 65,000 choices. So it doesn't happen every time, but if we're trying that for each number of buckets, for 1 to 65,000, ideally one of them lines up. And so what we'll do here is we'll start at this number, and we'll go down in the number of buckets. And when we get to the bottom, if we still, or no, let's say, the lower we go, the harder it is for it to happen, right? So if we find one, stop, that's where we'll stop. We'll take the last one we found. And this is actually, I didn't submit it as an issue, but that's not really optimal. Like if we miss one, we could still find ones that are lower. So I'm going to submit a PR later this week to update that so that if it misses, it still goes all the rest of the way down to see kind of the lowest it can find. But if it doesn't, then it flips into this tried exhaustive mode. It jumps the number of buckets up to the maximum and then starts going down from there. So eventually it finds one that solves this kind of like dense need, and then it does the same kind of thing. The only difference here is there's a bit more data that has to get passed back because we're not, we want to be able to basically grab all the data from that place at the end of code around the minimum call data size, if it's payable, that kind of thing, and then pull that into memory to do all the checks against, as opposed to having to like repeat the verbosity of doing all those checks at each place where a function is hit. So there's a lot of clever stuff here. I was sure that there would be issues, and I wasn't able to find any. There's a lot of kind of like clever things done to kind of make sure you're dispatching out to the right place later, grabbing the code, storing that as densely as possible, doing all the checks that are needed, and then making sure we're at the right function that we actually called, and moving on from there. So let's see. So that's creating kind of these chunks that represent all the external functions, right? We did all the parsing for the functions themselves. Then we did all this parsing for the jump table. Lastly, we do like fallback and constructor, or I guess fallback first, and then constructor. Fallback, obviously, if there isn't a fallback, then we want to replace that with reverting, because if they didn't fit any of the functions that we specified, that's what we want. And then lastly, an interesting thing here that I explored and then found was solved is these internal functions, it's making a bunch of assumptions in them that you're not calling from the constructor. But if it's an internal function, it could be called from the constructor. What they actually do is they just, for any internal function, if it's called from the constructor, they just put it in the bytecode again. So they'll be in there twice. Once that's kind of like in constructor mode, because that's not even deployed on chain, so it's not really a waste of bytecode. And then once that's like the proper internal one. So that's, let's see, generate IR from module. So we're making progress. I just missed it there.
What's up, guys? It's the next day. I kind of ran out of steam, so I'm gonna pick up here and get through the rest of the process. We're going a little long, so we'll try to keep this pretty quick. We just finished with the IR generation. So we got the all of the kind of like Vyper IR representing the program. The next step is to do optimization at the IR level. So we're going to do two different optimization phases. One is right now on the IR, and then later when we get to the assembly section, we'll do some other optimizations there. What you'll see here is it doesn't matter if the level is gas or code size. We do the exact same optimizations here. So let's jump in and look at what that looks like. So this is one of these like recursive sections where we're going to call this optimize function and then kind of go through the IR into each nested piece, or like the arguments of each piece, and call optimize on that, and kind of go down the tree and then back up the tree. And our goal is going to be that we kind of come up from the bottom of the tree, and only when a flow up from the bottom has no changes do we kind of like lock it in. And otherwise, we're going to kind of like redo those optimizations over and over until we get to a place where there are no changes. So what we can see here is like for every argument in a set of arguments, we're going to call that optimize function again. And let's actually skip this piece right here. We're going to go down to this finalize, which is called kind of after each round of optimizations. And we can see right here, if the args changed, that means like the sub arguments have had changes. This is if the argument itself or the node itself has changes. And so if nothing has changed in the node or below it, then we're going to return false and return the node itself. That is our way of saying like this part is done. If that's not the case, if anything has changed, we're going to replace it with this new node that represents the optimized version. And then we're going to call optimize on it again, right? So like I said, we want to keep doing this until there's no more opportunities. So imagine we're coming up from the bottom of the tree, it's locked in, it's locked in, it's locked in. Boom, we've got one with changes. Okay, so now we're going to skip this and finalize. We're going to replace the node with the optimized one, and then we're going to call it on this and go down the tree again and repeat it, right? Just making sure we get to a place where we can get up the whole tree, and I'm calling this a tree even though it's technically IR, I'm visualizing it that way, without any changes being made. So let's look at what the things that are done are before we call finalize. Right, so we can see a few different places where optimizations are done. The first is if the value is a sequence. So this is when there's like a set of actions that happen sequentially. And we don't have to get into all of these, but basically there are all ways of merging the memory You know what I'm realizing? Okay, I just popped over to another file. I was on a repo without any of my notes, so this will be better. So like I said, these are all different ways of kind of merging consecutive memory operations that could be just kind of put together into one big operation, right? Imagine we're copying code into this part of memory and then copying the code next to it into this part. Well, we could just copy that bigger chunk. And so these are kind of merging consecutive kind of like mem zeros, right? Like so for storing something at location 0. These are merging loading from call data. There's an interesting thing in here where this was a finding from the last audit, basically with the idea that if we're loading two things from like sequential pieces in memory, we can merge them together, except if, so this is like storing something in a location and loading something from another location. And it's saying, well, if they're sequential, we could move those together. The problem is if one of them writes into the other one, right? So if we're like saving it and then writing into it and then loading from that, that's going to give us the wrong answer if we merged it into one operation. So that's a really, really good finding. But yeah, so all of these are mostly focused on those kind of efficiencies. We've got this remove empty sequences. That's like, obviously if we have a sequence and then there's nothing in it, it doesn't do anything. So we can just get rid of that. And then this is saying, so if there's just one thing in args, I'll remind myself what args is. Right, the list. Okay, it's just the list of arguments. That Z threw me off. If there's just one thing in it, so if we have a sequence with one element, then it shouldn't really be a sequence. So it's saying basically just like strip off the sequence, take the first argument, and then call optimize just on that argument as opposed to pretending it's a sequence. And we can see after all this is done, so if it's sequence, we do these things, and then we call this finalize, right? So that's going to take us back up to here where we talked about where it checks, did any changes happen? If so, let's call it again. If not, let's lock it in and kind of move out one layer. Another type of optimization that happens are these arithmetic ones. So we can turn to this optimize binary operations. Basically what these are doing, it's kind of looking for stuff we can do at compile time. So like if both sides are literals, then we can actually do the operation, right? We caught a lot of these earlier, but sometimes maybe they've come up as optimizations have happened, things that weren't literals have turned into literals. So it can catch some of those. And then there's a bunch of things that if we even know the literal on one side, we can make some assumptions in certain cases. So looking here as an example, like we look at commutative ops, these are like add, multiply, right? Things that the order doesn't matter. So this is just going to put them in the order where the literal is second, so that we can always kind of assume that. And then we know, for example, like anything plus 0 or minus 0 or ORed with 0 is itself. So that's kind of locking in that optimization. And then if something is minus itself or XORed with itself or not equal to itself, we know that's not true. So it's just going through a lot of these things that if we know one of the values, or if we know the relationship between the values, like the same thing, we can make some assumptions there and simplify things. What I did with a lot of these, because like it's easy to reason about, but obviously it's scary that there's edge cases that could be missed where it might do something wrong. So I used, here, let's pop in here, this Halmos file. So Halmos is a really, really cool formal verification tool. It uses basically like Foundry syntax and abstracts what's happening into like for an SMT solver to solve like provably that it's always the case. So you can see here, I like took a lot of these, where is it here, like binary operations. I rewrote them in assembly to do the exact same thing, and then I tried to prove that they were accurate. So you can see I did a lot of those to basically verify that these optimizations are always safe to do. Right, let's see. And again, we're calling finalize on all this, right? So like we see that something is plus 0, we're gonna merge that into 1, and then we're gonna call finalize on it so that if it's changed, which it has, we go back down the tree and optimize all the way up again. So yeah, you can pop through these, but they're basically just like all clever optimizations of things that could be cheaper gas-wise if we know some piece of what's happening. Let's see. So those are the binary ops, and then we've got the bitwise ones too. So shifts, We can take some actions on ceilings, basically just like trying to do as much as we can at compile time, because obviously at runtime there's gas and at compile time there's not. If it's an if statement and we know which branch it is, get rid of the if statement and just use that branch. Static assertions that we know are going to fail, just don't compile if that's the case. So you get the idea. This is a really fun file to explore. So if we pop back out, let's go back to phases. Cool. So when all that's done, we have turned our abstract syntax tree into IR. We have run this optimizer over and over until there's no more optimizations we can do on the IR. And now we're going to return those files. And just for instance, like IR nodes, that's what's going to turn into bytecode. Runtime is this kind of like parallel path of compiling that is just looking at the runtime code, kind of ignoring everything that will happen like at deployment. It's actually such a useful feature to have, because sometimes we want to like etch code. If we're doing a Foundry test, like use vm.etch to put the code in a place, we don't want all the deployment code to be there. So, or if we want to even just like look at the IR and make sense of it, it's nice to ignore all the deployment stuff and just like look at the function logic. Cool. So when that phase is done, now we've got this IR output, and we can see, if we think about that whole flow of compilation that we talked about at the start, generate assembly is called with these IR nodes, which is basically just the first return value, the full thing, right? Not just the runtime code from what we just did. So we're now at that phase. I'm going to try to go pretty quick for the assembly and bytecode stuff, partially because there are a lot of details to get into and this is kind of long, and partially, honestly, because I spent a lot more time on the IR generation and kind of earlier steps, and so I probably won't have quite the level of detailed understanding of this stuff. But basically, there are just two functions that are called to do these last two steps. So in generate assembly, we can see this compile to assembly function does everything to convert our IR into assembly, which is like, you'll recognize a lot of the opcodes. It'll look kind of like opcodes, but then there's a lot of kind of like tags in terms of places to jump to and other instructions that aren't quite bytecode ready. And then for this generate bytecode function or step, we have this assembly to EVM. So we'll just go through those two, and then we'll be all set. So starting with the assembly one, we can loosely see, so same thing where we're copying it over because we want to keep those earlier stages in case we're trying to return them. We first rewrite these return sequences. So like the way these are written in IR is a little bit different. We want to make sure that we're doing this in a way that like sets the exit twos up properly. Basically is doing everything in the way that it will be in bytecode land. And then this is kind of the main chunk here, is compile to assembly. And again, it's the same structure where it's kind of a recursive call where each call then like goes into the nested things and calls it again and works its way up. So let me dive into that quickly. And one interesting mechanism here is that what we're doing, because one of the challenges is very often we're like creating a variable in IR, right? Like with X as blank, now we want to be able to reference X. And how do we keep track of that? Because like the way that's done on the bytecode level is that we are swapping or duping that value up from where it is on the stack up to the top to perform operations on. But how do we know where it is? And so the way it works is we're going through these nested calls all the way down, and we're keeping track of like the height, which is like how deep off of the like base are we in terms of like the stack variables. And if we know the height where a certain variable was declared and we know the height where we are now, we know where to dupe to in order to operate on that variable. So I won't go into too much detail here, but you can see some of the examples of what happens is like if the thing that we're dealing with on the IR level is an opcode, then compile, like go into that opcode and run this with the things in there. If it's an integer, then replace it with, here you can see what this push does, replace it with push and the length and then the thing, right? So like actually push it onto the stack. If we're setting variables, what do we do? If we pass, return nothing. So this is like all the stuff that could be in Vyper IR. For each one, what actions do we take in order to turn it into assembly? And then what nested assembly calls do we need to make for the next layer to happen? Repeat, we talked about this a little before, where like all those loops turn into repeats when they're in IR. And then what do we do with that? So we're like making a start of the loop, and we're actually jumping back all the mechanics of that are a little messier and less of a clean abstraction. So this is how all that repeat, like all the rounds get converted back. So like you could kind of piece together what the assembly is from like what are all the steps there based on the rounds. I did this a little bit, trying to make sure there were no bounds checks that could slip through. Break, continue. So again, like with, this is like when assigning variables in IR. So how do we basically like grab the right pieces from the stack to move up for that? Deployment, kind of putting through the code there. Sequences. So this whole big function is all of the different things that the IR can do and how we translate that into assembly. So once that's done, now we've got the assembly, we want to add post-ambles. A few things that happen here. We want to think about how many places in the code would end with like push zero, revert, right? We sent funds to a thing that should be non-payable, or there's any place where we catch an exception that we don't have like a specific error string, whatever. And so rather than putting all those in the code and increasing code size, we just have one shared version of that, and everything just jumps you to there if it wants you to revert. So that's one piece that happens here. Some other like pieces that are added in terms of like adjustment of the code. And then we want to relocate all the data segments. So like when we're doing the jump table and we're holding all that data in the code, making sure those are all moved to the end rather than like sliced in the middle of the code. And then if we have any optimization set, again, doesn't matter if it's gas or code size, we're calling this optimize assembly. And it's the same basic idea. This one has a cap of 1,024 runs that it can do, but it's the same idea where it's calling these specific actions. If any of them return true, then changed flips to true. And it keeps doing that until either we hit 1,024 runs or none of them return true and there's no changes, and then we move on. So we can quickly go through what these do. So we want to prune unreachable code. So like if there's a return statement or a revert and no way to get after it, we can get rid of that code. Merge as zero is interesting. So if we have a number and then is zero, what that's going to do is negate it and unnegate it. So we're going to end up getting a 1 if it's any value besides 0, and a 0 if it's a 0. So what that's doing is basically converting any value into a binary, or a Boolean, sorry. And so what this is doing is saying if the thing before it is already a Boolean, if we know it's going to be a 0 or 1, then doing a 0 does nothing. So we can get this list of return 0 or 1. These are opcodes that we know do that. And if they have a 0 like after them, we can just get rid of those. Merge jump test. So if we have like two next to each other, never a need for that. We can get rid of them or merge them. Inefficient jumps. So if we have like jump test and it's just doing that jump, we could just skip the jump and it will automatically be there. Unused jump test. So it goes through all the jumps and sees where they point. And if any jump tests aren't used, we don't need them. And then I'm not totally remembering what this is. I guess there's these patterns that come up in a few different situations and they don't do anything, right? If we're duplicating and then swapping and popping the top thing off, we end up in the same spot. And I guess this is something that happens for some reason in how the code is compiled. So just getting rid of those things. So that's how assembly is optimized. And then, then we got the assembly. So if you want to see an example of that, we can say, and you can see this looks a lot like opcodes, but there's these things like kind of that are kind of more values that we're going to end up subbing out for like specific opcodes and values. Cool. So then we got the assembly, and the last step here is to generate the bytecode from them. So we call this assembly to EVM, and it is going to go through here. Let's do this. Basically, it hallucinates. So it's got that assembly code, and it's going to go through each item in that assembly code, and it's just trying to basically reconcile like values that should be specific values, things that should point to specific places in code, things that reference how big the code is and the code size, putting the specific values, getting rid of basically anything that's like a pointer or a reference for us and replacing it with like what it actually needs to be at runtime. So you can see we're calculating like the literal runtime code, offset size. So like we're basically like everything that was loosely tagged as like an offset from a certain point, subbing in the actual values. Resolving those symbolic locations that we had, grabbing the deployment size. So it's doing everything to basically turn that into like bytecode, just 2 bytes per instruction, and then the values and like literally something that could be deployed. This insert compiler metadata we talked about before, so it's like converting it into the right format and sticking that suffix at the end that tags the Vyper compiler version and some other values. And then here's where it's actually doing it. Now that we've resolved everything, we now have assembly that like literally represents exactly what the bytecode should be, including that suffix at the end. We're going to go through and basically recall it on each piece in order to literally do those translations and like generate the actual bytecode itself. So I know that's a little bit vaguer. Honestly, if I had more time, this would be the place where I'd want to spend it. But that kind of gives a high level of what's happening there. And what's cool is like one of the other, so I guess if we do this, we could just say Vyper, and you can see like that same file, it gets compiled in this way, right to bytecode. The last step that isn't normally used, but if we want, right, like everything else, every other option in terms of output is something that we touched along the way. The one exception is that we can actually output opcodes, and that isn't a step along the way. It's basically a process of taking the bytecode and then for each opcode translating that into like the word opcode. Here, I'll show you what I mean. So, right, so this is literally the exact same as that, but translated into words. So if we go back to phases, and we can say, actually, you know what? Let's do. Here we go. So opcodes, and what that function is going to do is, it takes in that compiler data that already has bytecode, and then this build opcodes function is iterating through them and doing it. This was also a little interesting issue. So for most opcodes, it's going to look at 2 bytes. What instruction is that? Put it in. Look at 2 bytes, what instruction? And then if it's something that requires more value to be passed after, say it's push 2, well then it knows the next 2 bytes are the 2 bytes that are pushed from that, right? And it's going to kind of do that loop. So everything else is just verbatim. Push is the one exception, and then it's going to grab what's after it. The fun little issue there is the way this is converted is that it, let's see, it's getting the length of the thing that should be pushed, right? So like it says push 23, we know, okay, the next 23 bytes should be pushed. And then it's turning that into hex, turning each of those values into hex and merging them together with this join. But when you turn those into hex, they don't always stay 2 digits. So you might have some of those, if it's like 0.5, just become 5. Or if it's 0.0, just become 0. And then when they get merged together, that will be shorter than it would have been, and it'll end up kind of 0 padded at the front into a different value. So if we have like, if we're using this basically if we say push 23 and then the bytes kind of like start with zeros, we can end up with different values than we actually intended them to be. So I was like, I don't know if it matters a whole lot because the opcode thing, I mean, I guess it's there for a reason, but it's not like it's used for deployment. Cool, so that's a walkthrough of everything. If anyone's got questions or if you're exploring this in the future and want to bounce ideas around, I'm always available, but hope this was helpful.